So, have you ever wondered why deserts look wet, pencils break in water, sky is blue, but also orange, why there are rainbows, and they come in pairs, and why lunar eclipses are better than solar eclipses? Good. In the beginning, Maxwell said, or in other words, let there be light. And we have electromagnetic waves we call light. We'll ignore the waviness and look at light rays. Let's start shooting these light rays. Rays coming from a distant object, like the sun, will appear to travel parallel to each other. We'll start with a smooth, flat surface. Light will bounce off of a surface according to the law of reflection, which says the angle of incidence equals the angle of reflection. Or as Mr. Miyagi would say, bounce on, bounce off. A smooth surface keeps the rays parallel. This is called a specular reflection. Rays bouncing off of a rough surface scatter and appear to come from completely random directions. This is called a diffuse reflection. And this is why you see your reflection in a mirror, but you don't see your reflection when you look at a tree. It's also why you can't see yourself clearly when you fog up a mirror and it's no longer smooth, but you can once you wipe away the droplets. One bounce is good, but two is better. When a light ray bounces off of two mirrors that are at right angles to each other, the ray leaves in the exact opposite direction it came in at. This works in 3D too. We call these retroreflectors, or corner cubes, because it's the corner of a cube. And we put these on bicycle spokes. Say you're driving a car at night. The light from your headlights would hit the reflectors on the bicycle wheel and bounce almost directly back to your eye so that you see the bike. But since the light doesn't scatter in all other directions, it doesn't blind other drivers that might crash into you or the cyclist. That's out of this world. You know what else is out of this world? The moon. Let's say someone accidentally dropped a corner cube while riding a space bike across the moon. We could shoot a beam of light from a laser at the corner cube and have it return directly to a detector beside our laser. Since we know the speed of light and how much time passes between us shooting the light and it returning to our detector, we can accurately calculate the distance to the moon. Just when you think these mirrors are starting to get useful, they always seem to make my left hand look like a right hand. But how does the mirror know left from right? And why doesn't it flip up and down the same way? Well, the you in the mirror is facing the opposite direction of the real you looking at the mirror. And when you only flip the forward and backward directions, it's like turning something inside out. In other words, it changes the handedness. Righty-tighty becomes lefty-loosey. Speaking of this good-looking person in the mirror, the light rays from the object bounce off of the mirror. So we have to trace the light back behind the mirror to see where they appear to cross or where the image would form. For a flat mirror, the image is said to be virtual because the light we see does not actually pass through the image point. It just seems to because our brains can only interpret light as though it traveled in a straight line. What if we make the mirrors less straight? Maybe we could take a slice off of a shiny ball. If it's shining on the outside, it's a convex mirror. Now the light rays appear to cross closer behind the mirror, making the image smaller. Wait, the closer something is, the bigger it looks. So when things move far away, they should appear smaller. What if I think the object in the mirror is far away just because it looks small? Oh, that's why that's there. I wonder what happens when we make the inside of our ball shiny. Now we have a concave mirror. These tend to magnify as long as the object isn't too far away, so they're used by security and everyone's favorite people. All right, enough bouncy light. Light can also pass from one material to another. Not like that. Nope. Different materials mean they're made of different atoms with different number of protons and, more importantly, electrons. Light is fast when it's not being bothered, but electrons interact with light and make it less fast. So light is fastest in a vacuum, slightly slower in air, noticeably slower in water and glass, and it crawls through diamond, which is why these guys aren't cheap. A material's index of refraction is represented by the letter N. It's the ratio of the speed of light in vacuum to the speed of the material. The bigger the N, the slower light. The smaller N, the faster light. But light never goes faster than in a vacuum, so N is at least 1. But changing speeds also causes light to bend when it crosses materials. This is called refraction, as in index of from before. But why does it bend? To explain, we'll go on a side quest. Imagine you're on a beach and your friend is in the ocean, about to get eaten by a shark, a scary shark. They only have so much time left. You head straight for your friend because you know the shortest distance between 2 points is a straight line. Yes! And surely traveling the shortest distance will get you there in the least amount of time. Wrong. Now that your friend is fish food, we can think a little bit more carefully. You probably can't swim as fast as you can run. So you want to spend more time where you're faster and less where you're slower. You made the path a little bit too long, but maybe somewhere in the middle there's a sweet spot. That's it. Your speed and angle you should take should follow Snell's law. That's right, a guy named Snell tells you the fastest path. This is called the path of least time, and this is the path that light takes, and it bends or changes directions to make this happen. So light, unlike you, would always save their friend. Inside quest. We draw a line perpendicular to where two materials meet. Light bends toward this line when moving into a slower material and away when entering a faster material. All of this physics is making me hungry. Let's go catch a fish. No, not with that, with this. We see a fish in front of us, but keep missing. The light from the fish is coming up, bending before it hits our eyes. Our brain assumes the light is traveling in a straight line, so aim down. Like my favorite quote, give a man a fish and you feed him for a day. Teach a man Snell's law and you feed him for a lifetime. Still tired of missing the fish? Get directly above the fish and light won't bend. It bends more the further you get away, until eventually no light makes it out at all. We call the critical angle where this happens the critical angle. Beyond this angle, light actually bounces back inside. This is called a total internal reflection. Have you noticed you can only see underwater so far before it's just reflections of the sky? Good news, you don't have bad eyesight. I mean, you might, but that's not what's going on here. You can see up close, but eventually light coming from objects under the water are beyond this critical angle, and so the light never comes out and makes it to your eye. Now that we know some of nature's tricks, we can use them for ourselves. If we pass light through a triangular prism, it will pass straight through this surface, internally reflect at this one, and leave in the opposite direction. Then we can pass it through another. We package it all up, add some magnification magic in the middle, and look, binoculars. Sometimes we want to send signals through cables. A special material makes the light always internally reflect, so no light leaves and no signal is lost. And we can put them in the ground and run them around in any direction we want. We call these fiber optic cables. And remember these? Light slows down so much in diamond, it's easily internally reflected. So light comes in, bounces around, and appears to leave randomly, making it sparkle and expensive. Now let's visit the wavy light for a second. Light can have different wavelengths and frequencies or cycles per second. These come together to give the speed of light. But since the speed of light is always constant, if one of these increases, the other decreases. We perceive shorter light as blue and longer light as red. And this dude Roy G. Biv tells you where the other colors come in. Shorter, bluer light bends more when passing through a prism because it slows down more. This causes all of the different colors to spread out into a rainbow of colors, and this is called dispersion. You probably know what's coming next. Rainbow doesn't often fall in the desert. But why does hot sand kind of look wet? The hot sand causes the air directly above the sand to be hotter than air further up. As you go higher and higher, the air is slightly cooler with the coolest air at the top. How did I still end up with a rainbow? Anyway, cool air is more dense, and more dense means light will be slower. But light always takes the path of least time, so it casually bends through the layers of faster, warmer air before coming to your eye. This happens with light from faraway objects, and since we think light is traveling in a straight line, the object appears on the ground. Remove the object, and it still happens with light from the sky. I call this a sky puddle, but you may call it a mirage. Now to rainbows. After it rains, droplets of water fill the air. When light hits the droplets, they act like a prism and cause colors to separate. Some light then passes through, but at the right angle. Some is internally reflected and comes out the other side where we can see it. Now these raindrops are really small, so you probably only see one specific wavelength or color from any given drop depending on the angle it's coming out at. Someone next to you seeing that droplet from a slightly different angle, they may see a different color. If they're far enough away, it may be completely different rain droplets that form their rainbow. So in other words, you get your very own rainbow.
Aww.
No, not all. This means that as you move, the rainbow moves with you, and it stalks you like a crazy extra. But wait, there's another rainbow. It looks inside out, and like it's been in the sun too long. Light entering some droplets begins like before. Some lost, some reflected, and then it bounces again, losing even more light. The remaining reflected light then crosses its original path before leaving. This causes the colors to get flipped upside down. So the second rainbow is always more faint, and it's always flipped. Now to fully control light, we need thin lenses. Like a mirror, a lens is either convex or concave. Light from really far away will converge when passing through a convex lens and diverge when passing through a concave lens. If you haven't seen a convex lens, you've definitely seen with one at the front of your eye that focuses light onto your retina. This is a healthy eye, but if your eyes focus light in multiple spots, you have an astigmatism. If you focus light too close, you're nearsighted, and if you focus too far, you're farsighted. If you see it all, you notice the sky is blue. But why? We only see the light after it scatters off of air molecules and hits our eyes. This is called Rayleigh scattering, and according to Lord Rayleigh, the probability of light scattering increases as the wavelength decreases. But it's to the 4th power, so blue light scatters everywhere, and there's so much you'll never see the redder light during the day. But what about at sunset? The light hits the atmosphere at an angle, so it travels through more air. All of the blue light scatters first, and by the time the light gets to you, the blue light is gone, and all that's left is the redder light. These sunrises and sunsets form a ring and move as the Earth spins into and out of the sun's light. Every so often, the Earth gets between the sun and the moon, and we call this a lunar eclipse. So the Earth blocks the moon and it disappears? Not quite. Since light moves ever so slightly slower in air, it bends a little inward and goes through Earth's atmosphere, and it gets directed onto the moon. Remember, all the blue light scattered first and is gone, so what's left is the red light from sunsets and sunrises getting projected onto the moon. Take that, solar eclipse. And finally, speaking of things we see in space, telescopes use lenses to magnify faraway objects. Let's see what else is out there. Ooh. Don't forget to like and subscribe.